Hello, everyone. My name is Marie Morrow. I am a graduate assistant here at the Map Zone at the University of New Haven. And today we're going to be looking at the applications of linear functions. We have three learning objectives that we're going to be looking at today. Number one, we're going to be understanding the concept of linear functions. We're going to understand the visual representation of linear functions and how to solve them, and identifying and describing real-world applications of linear functions. A linear function is that is represented by a straight line, typically in the form y equals mx plus b, or f of x equals mx plus b. F of x is the function. For slope, it can also be known as m, and it is the rate of change. M is the measure of the steepness of the line. So, for example, if the line is 5, it's going to be steeper than a line that has a slope of 1. So the larger the number for m, the steeper the slope. And it is calculated as the change of y over the change of x, rise over run. B is the y-intercept, and that is the point where the graph intersects the y-axis. And at that point, x will equal 0. The domain is all the possible values for the function, and the range is all the possible y values for the function. So domain is all the possible x values, range is all the possible y values. And you see here for this little formula, y is the dependent variable, while x is the independent variable. The independent variable is what we change throughout the equation. So for example, a time versus distance graph, the time will change and the dependent variable will change according to the change in the independent variable. So it is dependent on the independent variable. So these are the steps on how we solve linear equations. Step number 1, we're going to simplify the equation as much as we can, and then we're going to move all the variables to one side, and then move the constants to the other side. Then we're going to isolate the variables, and once you get your answer, you're going to replug it back into the original formula to check your work. So this is a visual representation of a linear formula and its graph. So again, this is time over distance, a very common linear function that we see in science. And as you can see here, the time changes by every second. And as that happens, the distance changes by 20 feet. And so you can see here that the y-intercept is 20, and at 20, x equals 0. So again, the formula is y equals 20x plus 20 because the slope is that it changes every 20 feet, and so therefore it would be 20x. These are linear equations that can be used in the real world. So in science, we can use it for temperature conversion, physics motion, chemistry concentration problems, biology linear population growth, and in business, we can use it for budgeting, business profit, supply and demand. And in everyday life, there's so many examples, but some include grocery shopping, travel planning, and fitness tracking. This is a real example problem. The temperature in Celsius is given by the equation C equals 5 over 9 F minus 32, where F is the temperature in Fahrenheit. If the temperature is 68 degrees Fahrenheit, what is the temperature in Celsius? So we know that Fahrenheit equals 68 degrees in this problem, correct? The next step that you're going to want to do after you identify what Fahrenheit is plug it into our equation, which is given to us in this problem. So 5 over 9, in parentheses, 68 minus 32. And first, you're going to want to solve what's in the parentheses. So 68 minus 32 equals 36. And next, since we are dealing with a fraction, we can multiply 36 times 5 first and get 180 divided by 9. And 18 divided by 9 equals 2, and add the 0, we get 20 degrees Celsius as the answer. Real example number 2. A shoe company found that if it spends $40,000 on production, it can produce 10,000 pairs of shoes. Each pair of shoes is then sold for $60. So we're going to create a linear function to represent the profit, P of x, where x is the number of pairs of shoes sold. What will be the profit if the company sells 7,000 pairs of shoes? So let's go through this problem. Number 1, let's identify what the total revenue function is. So r of x equals 60x. So dependent on how many shoes that we sell. And we're gonna figure out the total cost. So we're spending, again, $40,000 on production. That is a cost. And let's put it all together to get the formula that we can use for our linear function. So P of x equals R of x minus the cost. So again, our P of x is the profit. And R of x, that is our revenue, how much we are making before we subtract the cost, which again, C is the cost. So it's important that we remember to include that because that is how we get our total profit. So let's put it all together and include our values. So P of 7,000 equals the revenue, 60x. And we know that x is 7,000 pairs of shoes because that's how many we are selling, minus 40,000. So first, let's multiply 60 times 7,000. So 6 times 7 equals 42. And all you're going to do now is just add in the zeros and then subtract from 40. And then we'll do that in the next step. So 420,000 minus 40,000, you're going to get $380,000. And do not forget to include the dollar sign in problems like this. Thank you all for listening to my lesson today, and thank you for watching.